In this video, I'm going to introduce the photoelectric effect. This effect and the discovery of it is one of the greatest discoveries of the 20th century. And it took some of the greatest minds in physics, including Einstein, in order to explain this to humanity. Before we delve into the photoelectric effect, let's first revise some basic concepts pertaining to light and the electromagnetic spectrum. Now, in grade 10, we learned that visible light, that is red, orange, yellow, green, blue, indigo, and violet, the light that we as human beings can see, forms a very, very narrow band on the full electromagnetic spectrum, which ranges from radio waves, which have wavelengths that can be several kilometers, to gamma radiation, which has wavelengths that are of the order of magnitude of the size of a nucleus of an atom. Now, this electromagnetic radiation is all formed by accelerating particles. Now, when these particles accelerate, they produce alternating electric and magnetic fields which induce each other. What I mean by that is that as the electric field changes, it creates a magnetic field, and as the magnetic field changes, it creates an electric field. And these inducing electric and magnetic fields are able to propagate electromagnetic radiation through vacuum. So these are very different waves to, for instance, sound waves, which need a medium, or the waves that are created in a slinky when we vibrate a slinky, because these waves are not mechanical waves, and they therefore do not need a medium. There's also something very specific about these particular waves, and that is that they all travel in vacuum at the speed of light, which is 3 times 10 to the 8 meters per second. That's 300,000 kilometers per second. Now, to give you an idea of how fast that is, the circumference of the Earth is approximately 40,000 kilometers. So if light travels at 300,000 kilometers per second around the Earth, that would mean it could circumnavigate the Earth 7.5 times each second. The photoelectric effect is defined as the ejection of electrons from the surface of a material, in particular metal, when light of a sufficiently high frequency shines upon it. And the electrons that leave the surface are referred to as photoelectrons. They are no different to any normal electron. They are electrons, they have the same mass, they have the same charge as the electrons in the metal, but we just refer to them as photoelectrons because they have been ejected from the metal surface because light rays or electromagnetic radiation has shone on them. The flow of these electrons is called the photoelectric current. Now, a little bit of historical background. Heinrich Hertz was the first to discover the photoelectric effect in 1887 when he was busy investigating radio waves. Now, we've heard the term Hertz as a unit for waves, for the frequency of waves, and it's named after Heinrich Hertz, who did research into waves and radio waves. And what he noticed was that a spark would jump further if the metal surface was illuminated with ultraviolet light. Now, in the video that preceded this, it was demonstrated that when normal visible light was shone onto the surface of the disc of the electroscope, that no electrons left the surface. But when ultraviolet radiation was shone onto the disc of the electroscope, that electrons indeed left the surface, and therefore the deflection of the gold leaf actually reduced. Now, we cannot explain this phenomenon if we view light as a wave. Now, historically, in 1901, Max Planck showed that the energy of light is indeed quantized. By quantized, we mean that it comes in discrete quantities. And this particular relationship here, E equals hf, where E is the energy of the electromagnetic radiation, H is Planck's constant, which we will delve deeper into at a later stage, and F is the frequency of the electromagnetic radiation. A physicist by the name of Philip Lenard carried out further experimental investigation, and this won him the Nobel Prize in 1905. But at the end of the day, it was Albert Einstein who explained the photoelectric effect, and this eventually won him the Nobel Prize for physics. So why does the wave theory of light not explain this phenomenon? Well, as we've already referred to, electromagnetic radiation consists of two components to its wave. There's an electric field component, and then 90 degrees to it is a magnetic field component. Now, the electric field component, as it hits the surface of a metal plate, would actually cause the electrons on the surface under its influence to wobble. And over a period of time, as this wave continues to act on the surface, the electrons would gain more and more energy until eventually they would be able to break free from the surface, much the same as a water molecule that has enough energy is able to leave the surface of water. Also, if electromagnetic radiation of a high enough intensity were to be shone on the surface of the metal, then the wave theory of light would predict that it would cause the electrons on the surface to wobble so much that they would break free. So the wave theory of light predicts that all frequencies of light, all frequencies of electromagnetic radiation, should be able to eject electrons from a very shiny, clean metal surface. Now, as we have seen in the demonstration in the video that precedes this video, that is not the case. Visible light, no matter how intensely you shine it on the surface of the disc of the electroscope, does not eject electrons from the surface. But ultraviolet light, even of a very low intensity, ejects electrons from the metal surface. And this was a massive problem for physicists at the beginning of the 20th century. For hundreds of years, physicists had believed that the fact that light is a wave was a proven scientific fact. The fact that we could explain phenomena like the diffraction of light, the fact that we could mathematically explain that light was made up of electric and magnetic fields that continually varied and alternated, was a proven scientific fact. Yet here, with the photoelectric effect, this particular model of light could not explain this phenomenon. I'm making use here of a PhET simulation to simulate the photoelectric effect. And it has a representation of the basic setup of the apparatus. This is a glass tube that has a partial vacuum in it. We have two metal plates that are connected to a variable voltage source that not only the magnitude can be changed, but also the polarity can be switched around. At present, the negative pole of the battery, or the negative terminal of the battery, is connected to this metal plate. And on the metal plate is a particular metal, shiny metal surface that has been placed there. In this case, it is zinc. On the other side is another metal plate which is connected to the positive terminal of the battery or the voltage supply. Now, because of the fact that the metal plate here is connected to the negative terminal of the battery, this becomes the cathode, and it has an excess of negative electrons on its surface. The zinc plate that is on its surface will obviously also have an excess of electrons because it's connected to this plate. So this is the cathode. And on this side, there is a depletion of electrons, so there's excess positive charge on this plate, and therefore it's called the anode. So there will be an invisible electric field that would flow in this direction for positive charge, and negative charge would flow in that direction. we are starting off with a very low frequency electromagnetic radiation being shone onto the metal surface. And what we're going to do in this simulation, we are going to look at the energy of the electrons that will leave the surface, if and when they leave the surface, being plotted versus the frequency of the incident electromagnetic radiation on the plate. Now, when we refer to incident, what we're meaning is incoming, falling on to that metal surface. So now, as we move the button across, we are shining higher frequency electromagnetic radiation onto the surface of the zinc metal. And we're not finding any electrons coming off the surface until we get into the UV range. And this is what Heinrich Hertz found. He found that when UV radiation, high frequency electromagnetic radiation, was shone onto a zinc surface, that electrons, sparks, jumped across. Now, this little reading here is in nanometers, so that is not frequency, but that is wavelength, and we will use that later on in our calculations. And what we're finding here is that there is a threshold wavelength where electrons start to leave the surface. This is an intensity button. As the intensity increases, it just means that we're making the incident radiation brighter. We're shining more light energy or electromagnetic radiation onto the surface. Now, in the blue range and in the yellow and green range, we find no electrons leave the surface. And this is where the wave model of light broke down, because according to the wave model of light, if you shone a bright enough ray of light onto the surface, electrons should jump off the surface. But we find here that it's only in the UV range that this happens. So this points to a minimum frequency required in order to eject electrons. Now, what we're doing here is we're applying a retarding potential where we're switching the electric field around. This becomes the negative and this becomes the positive plate because we've switched it around. And the idea here is by switching the electric field around, you're creating a field that's slowing down the outcoming electrons. And the reason for this is so that we can measure the energy, the maximum kinetic energy of the electrons that are leaving the surface. And so for zinc, there was a very specific frequency and wavelength at which electrons started to leave the surface. And this frequency is referred to as the threshold frequency, and the associated wavelength is the threshold wavelength. And we'll be using these extensively in calculations in the next video that follows this particular video. So why the threshold frequency of the incident electromagnetic radiation? Why this minimum frequency for electromagnetic radiation in order for electrons to be emitted from a particular metal surface? And this is where the brilliance of Einstein shone through once again. He proposed the quantum theory, or the particle theory of light. And what he said in this theory is instead of viewing light as a wave, is to view light as particles of light, or photons of light. Photos means light in Greek, so photons would be particles of light. Quanta of light, meaning coming in little packages of energy. That light is made up of particles of light. So you could think of it like firing a machine gun with high velocity bullets, one after the other. You can view a ray of light as a ray of bullets of light energy, one after the other, impacting on the surface. And each of these quanta of light would have a very specific energy which would be directly proportional to the frequency of the electromagnetic radiation. Now, often in physics, we find these very simple formulas. They seem simple on the surface, but in actual fact, they're profound. Think of E equals mc squared. We actually developed atomic bombs and nuclear fission, and we've got nuclear reactors today based on E equals mc squared. Truly a profound formula. And the same is true of this one, E equals hf, because on the right-hand side, frequency is a property of waves. But on the left-hand side, this energy here is quantized energy. Remember, we referred to the fact that Planck derived this relationship. So we have a particle property on the left-hand side, quantized energy, and on the right-hand side, we have a wave property. And the proportionality constant is Planck's constant, 6,6 times 10 to the minus 34 joules seconds. And this is the smallest constant, physical constant, that we will work with. And it basically, it shows the relationship, or what it does is it helps to link the particle nature and the wave nature of light in a truly profound way. Now, to fully explain this, I'm going to refer to the metallic bond. But before I do that, I just want to mention something. This symbol that I'm using here, please be careful with this. This is just a representation. This is not meaning that a photon has got a little wave in it. I'm purely using this to represent the duality, the wave-particle duality of light. So light does have wave properties, and please do not think that the photoelectric effect is negating the fact that light behaves as a wave under certain circumstances, because it's not. Light is both a wave and a particle, and that is truly something difficult for us to actually come to terms with. But the reality, or certainly the way we perceive the reality of light at the moment, is that it has a particle and a wave nature. And so too it's true of electrons. Electrons are both particles and waves, and this too is a proven scientific fact. So let's try and understand this using first principles. So let's consider a metallic surface. In this case, let's say a zinc surface, like the zinc plate on the top of the electroscope in the video that precedes this video, and the zinc that was in the simulation. And zinc, being a metal, is made up of a lattice of positive metal ions, referred to as kernels sometimes. And what these are, in actual fact, are metal atoms which have lost some of their electrons, which have become delocalized. So these are electrons. And in grade 10, we refer to these electrons as a sea of delocalized electrons. Also referred to as a Fermi sea in university physics. So there's a sea of delocalized electrons, which are negative, and then there is this crystal lattice of atoms that have lost their electrons, and therefore they have a net positive charge. But please note that they still have electrons in them. They just have less electrons than they have protons, therefore they have a net positive charge. Now, the metallic bond comes about because of the attraction between the sea of negative electrons and the positive lattice. So that is the metallic bond. Now, that's a force. That's a force of attraction between positive and negative charge. It's a Coulombic interaction, as we've learnt about in grade 11. And in order to overcome it, there is a minimum energy required to be given to the electron in order for it to break free from the attractive force of the positive metal kernels. Now, if we have a photon of, say, for instance, yellow light coming in, it has a particular energy, E equals hf. Now, as this photon comes in, it hits this electron, and the way it works, it gives all its energy to that electron. It's a one-to-one relationship, and that's very important. So what we mean by this one-to-one relationship or one-to-one correspondence is that one photon gives all its energy to one electron. So a high energy photon will not be able to give its energy to 2 or 3 electrons. It is a 1:1 collision. So one photon collides with one electron, giving all its energy to that electron. Now, in the case of a zinc surface, as we've already seen, a yellow photon of light is not going to be able to eject electrons from the surface. So the frequency of the photon is less than the threshold frequency or the minimum frequency required for zinc. Now, the reason for that is that the energy of the photon is less than the minimum energy required in order for the metallic bond to be broken. So there is a minimum energy that is required in order for the Coulombic interaction between the electron and the positive metal ions to be broken. And in the case of a yellow photon, that energy is less than the minimum energy required. So that means the electron does not leave the surface. So either the photon is then absorbed by the zinc and it basically doesn't leave the surface, and so the internal energy of the zinc increases, or what happens is the energized electron re-emits a photon and it reflects off the surface, which happens a lot with shiny metal surfaces. Now, a mathematical way of writing this is to say the following, is to say that, well, let's refer to the minimum energy as W0 or WTH for threshold energy, and that's going to be the minimum energy, and we have a fancy name for this. We call this the work function of the particular metal. So this would be the work function of the zinc. That is an indicator of the strength of the metallic bond. So the stronger the metallic bond, the higher the minimum energy required for an electron to break free from the metal kernels, and therefore the higher the work function of the metal. Now, when we look here, we see that this photon has an energy that is less than the work function. So mathematically we can write this as E photon is less than the work function, or as H times the frequency of the yellow light is less than the work function. And we will come back to this at a later stage. Now let's look at what happens when a photon of ultraviolet light that has a frequency higher than the threshold frequency hits an electron on the surface of the metal. So I've enlarged the representation of the electron and the zinc metal ion and the photon. Now, it's so easy to develop misperceptions or misconceptions of the photon. This symbol, once again, I'm going to mention it again. This is just a symbol to represent a photon. I've used a particle and a wave. A photon is not a particle that has a wave in it. Neither is it a particle that has a physical dimension to it. So it's a packet of energy. Now, with UV, we know that UV light emits electrons. So the frequency of the UV, and let's say it's FUV, times Planck's constant, is going to give us the energy of a photon of ultraviolet light. So we're working now with a single photon of UV interacting with a single electron according to that 1:1 correspondence we have spoken about. Now there is this attraction between the electron and the metal kernels, and that is the metallic bond. And for clarity's sake, remember this formula from grade 11. The Coulombic interaction, Q1 would be the electron and Q2 would be the positive metal kernel, and we are oversimplifying this purely for us to be able to come to some form of conceptualization of what is happening. But so often in physics, the models that we use to try and grapple with these complex phenomena are simplifications, oversimplifications of the true reality. So looking at this now, when this photon interacts with this electron, it gives its energy to the electron. Now, the energy that it gives to the electron results in the photon disappearing, because remember, the photon is not matter. It's not a matter particle. This is a particle of energy. And when the energy is given to the electron, the photon disappears. Now that electron has enough energy to break free from the surface. So we're going to represent this electron now as breaking free from the surface, and it would now be what we call a photoelectron, and it does not mean that in any way it has changed to a different particle. We are just referring to it as a photoelectron because it has been emitted by a photon of electromagnetic radiation. Now the reason why that happened is because the frequency of the photon, the UV photon, is greater than or equal to the minimum threshold frequency. Now, if we multiply this on both sides by h, then what we get is h times frequency of UV is greater than or equal to h times the frequency threshold. And on the right hand side here, this is the minimum energy required for a photon to emit an electron from this particular surface. So in this case, this is the work function of the zinc. And this is just the energy of the photon. So the energy of the photon is greater than or equal to the work function of the zinc. Now, in order to quantify this as what Einstein did, we need to consider three fundamental components to this phenomenon. The first component is the photon. This is the incoming energy, as it were. The second component is in actual fact the metal. It's the metallic bond strength of the metal ions on the electrons on the surface. And the third component is the photoelectron which leaves the surface. Now Einstein developed or constructed an equation which we are going to use in order to solve photoelectric effect problems in this course, and he used energy conservation. And the way I'm going to put this forward is as follows, that the energy in is equal to the energy out. That's what conservation means. It means that something is conserved, something is constant, and so in this case it's energy. Now the energy in is the energy of the photon. So we're going to write here E photon, and remember that is component 1. That is the energy coming in, and that energy is given to the electron, and the electron now has to pay, as it were, an energy toll. Now if you travel on a road, certain roads are what they refer to as toll roads. You have to pay a tax, or you have to pay a certain amount in order to be able to drive on that road. Now for the electron to leave the surface, it has to pay an energy tax, or an energy toll, as it were. And that energy toll is the minimum energy required for an electron to leave the surface. So this term here represents the second component of this phenomenon, namely the metallic bond of the zinc metal. The third component is the electron that leaves the surface, and it has an energy. And that energy is in the form of kinetic energy. Kinetic energy is the energy that a body possesses due to its motion, and it's equal to half the mass, and in this case it's the mass of an electron, which is a known constant. It's extremely small, but it is known and we can use it, times the velocity squared of the electron. Now, electrons cannot be seen, so the way we determine the electron's velocity is experimentally, and the way that we do it is by applying that retarding potential that I showed in the simulation. Now, with that retarding potential shows us what the energy is of the electrons that have the maximum kinetic energy. So we put max here in the subscript because we cannot measure the kinetic energy of electrons that leave the surface that have energy less than the maximum kinetic energy, and that's an experimental constraint, because the retarding potential stops the electrons that travel the fastest through the space between the cathode and the electrode. So if you stop those, then electrons that have a lower energy also don't reach the anode. So, but we cannot measure those velocities and those kinetic energies. We can only measure the maximum kinetic energy for the electrons that have the highest velocities when they leave the surface of the cathode. So we have the third component. Now this is a very, very, very important and very powerful equation which Einstein derived and which we, as I've mentioned, are going to use. And we can expand on this by doing the following. We know that the energy of the photon is given by Planck's constant times the frequency of the electromagnetic radiation. So I'm going to replace this term with h times the frequency of the photon, which then equals the work function, which we can replace with h times the threshold frequency, plus the kinetic energy, which we can replace with a half the mass of an electron, and all electrons have the same mass, times the velocity squared of the electron. And remember that we can only determine the velocities of the electrons with maximum kinetic energy when leaving the surface, so we're going to put a subscript max in there. And we are going to end this video with the equation in this form. And I always find it quite ironic that Einstein played such a critical role in providing a theoretical foundation for quantum mechanics in the 20th century, because he wasn't a fan of quantum mechanics by any means. But are we not thankful for the fact that he did this? Because this also helped other scientists to move forward with quantum mechanics. And this particular theoretical framework helped to form a theoretical foundation for technologies like photocells that we use extensively today in our world. So thank you, Professor Albert Einstein.